Start today with 7.4 division properties of exponents, but before we do, I want to review the multiplication properties, and those were a to the m times a to the n is a to the m plus n. When I had multiplication, I was going to add the exponents. So if I had x squared times x to the fifth, we knew that was x to the 2 plus 5, or x to the 7th. Another such example involved the coefficients. And true to our property up here, we were going to add the exponents, but we multiply the coefficients. And the little jingle is to multiply the bigs and to add the smalls. Multiplication went with addition. Division is the opposite of multiplication. So those division properties says something different, or the opposite of. Again, up here with the multiplication, if I have the same base, I added the exponents. So the division property is going to be the same base subtract exponents. And by division, I want to remind you, all fractions are division problems. All fractions are division problems. So if we write that in an algebraic notation, it's going to look like a to the m over a to the n. That says division. In this case, I am going to subtract the exponents. So we also have coefficients, and if I multiply them up here, I'm going to divide the coefficients. This is also reducing, and we talked first semester about when I reduce, I'm going to use 2 and 3 and 5 to divide into those coefficients. Okay? So another bit of really important information here is to talk about algebraic fractions. Now obviously this is something that has a numerator and a denominator. It's a fraction, but what makes it algebraic is that it has variables and coefficients and exponents all in there. So there's some very important things that we have to realize, that the numerator is a problem by itself. I have to simplify, or make sure it is simplified before I go on. The denominator is a problem. And again, I have to simplify it. Then there is a problem between the numerator and the denominator. Okay? And again, as I said, there are a little bit of information and lots of examples today. Lots of examples. And we're going to begin here with the first one. Very simple. Five to the fourth over 5 cubed is 5 to the 4 minus 3, or 5 to the first. And I hate to bring it out so quickly, but the second problem has a twist to it. I have negative 6 cubed over negative 6 cubed. Now, the part that the exponent's acting on is this base that's inside parentheses. It is similar in the denominator, and any number over itself is equal to 1. Okay? These bases are inside the parentheses are exactly the same. So it's the same example over here. Okay? The next is 8 squared times 8 over 8 to the 5th. Now, with this one, remember, we got to put in that 1 that's there. It's not written. And this is an example of what I'm talking about where the numerator is a problem. Is it simplified? It is not. So I do have to simplify it first. The denominator, yeah, that's simplified. So the numerator is a problem, the denominator is a problem, and now the problem between them. This gives me 8 to the 3 minus 5, which gives me 8 to the negative 2, which is 1 over 8 squared, which is 1 over 64. Now that's a lot of steps. That's a lot of steps. When I have division, I find myself asking the question more often than not is, which one has more? So if I take this problem right here, 8 cubed over 8 to the 5th. There are 3 factors of 8 in the numerator, 8 times 8 times 8. And there are 5 in the denominator, 8 times 8 times 8 times 8 times 8. There are obviously more in the denominator. How many more? 2 more. They cancel out with 3 of those in the numerator, and my answer is 1 over 64. Okay? So similar to that is the next example, which is 3 squared times 3 to the 4th over 3 to the 9th. And again, this numerator is not simplified. So the numerator has to be simplified before I can apply the property. So that's 3 to the 6th over 3 to the 9th. And I ask myself, which one has more? Well, they both have a base of 3, so as I compare these, there are 3 more in the denominator than there are in the numerator. And I must simplify 3 cubed to be 27. Okay? Everybody all right with that? The next one, likewise, Kind of plays into that same property, that same trick. I have 2 squared over 2 to the negative 3. Now 2 squared is fine, but I got to move this negative 3 across the fraction bar and make it a positive 3. And when I do, there's a 1 in the denominator, or nothing. I add these because it's multiplication. Multiplication and addition go together. So my answer is 2 to the 5th. And I have to multiply 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Okay? Now, again, comparing these numerators to denominators works the same when I have variables and variables only. I am comparing x's to x's, and I'm going to see that I have 2 more in the numerator than I have in the denominator. As far as the y's go, there are 2 more in the denominator than there are the numerator. So I've simplified that one. Again, as we talked the other day, what happens? We just give you more stuff, more things to compare and deal with. Again, here you are comparing A's to A's, B's to B's, and C's to C's. And you see that there are 4 more A's in the denominator, there are 2 more B's in the numerator, and 7 more C's in the numerator. Okay, any questions there? All right, the next thing I want to do then is to review the power quotient. And I loop this together with the product quotient because it is the same thing. You're taking the exponent on the outside of the parenthesis, and you are multiplying it or distributing it to each of the exponents on the inside of the parenthesis. So you have a to the MP over b to the NP. And again, this is something we talked about the other day. So this part should go relatively smooth. Throw up your hand if you have a question. But I have 2/3 cubed. These each have an exponent of 1. So when I multiply those, I have 2 cubed over 3 cubed, and I must simplify this to 8 over 27. One over x cubed. Again, don't forget that this has a 1 as an exponent. So this is 1 cubed over x cubed, which is 1 over x cubed. X to the 4th over y cubed raised to the 5th power. I am going to multiply that 5 times the 4 and 5 times the 3 to get x to the 20th over y to the 15th. Similarly, I have 2x squared over 5y to the 7th. This whole product is squared. I have an exponent of 1 on the 5 and a 1 on the 2. And I'm going to take this 2 and it's going to multiply times each of those exponents and give me 2 squared x to the 4th, and multiply it down here and get 5 squared y to the 14th. I must simplify these coefficients here as 4x to the 4th and 25 y to the 14th. The next example is a starred example. C squared a to the 5th over a cubed squared. Now this is a starred example because I could dive into this, but I need to follow my rules of operation. I need to do PEMDAS. And you say, I thought we were. Well, we were. We haven't had a situation like this before. But inside of the parentheses, we can simplify. Comparing the A's, there are 2 more A's in the numerator than there are in the denominator. And the c squared doesn't compare to anything. So I have a squared c squared in the numerator, 1 in the denominator, and when I multiply these exponents, I am going to end up with a to the 4th, c to the 4th. So the rule is, or the thing I'm trying to get you to realize here and do, is to simplify inside parentheses first. Before you start applying the E or exponent rules, simplify inside the parentheses first. And that is why that is a starred example. Because of this note, you have to look inside those parentheses and see what it is you can do. So we're going to talk about a couple more of these, just to pick up the different ways that it can be kind of screwy. If I have x to the 5th, y squared, z to the 7th, over x squared, y to the 8th, z cubed, and that quantity is cubed, I am going to compare x's, y's, and z's. There are 3 more x's in the numerator. There are 6 y's in the denominator. And there are 4 more z's in the numerator. All of that is cubed. All of that is cubed. But I've simplified inside the parentheses first. And now I would do the other part, excuse me, and multiply these exponents. X to the 9th, z to the 12th, y to the 18th. And again, this is a very tedious area, so I'm going to draw attention to this last example with a double star. 4x to the 5th y squared over 20 x y to the 9th all squared. Now the reason this has a double star is because of these coefficients. Yes?
What if they're not lined up like y's under y? Like
Can you talk this way? What?
So like if y is like over x, like they're rearranged, can you still like simplify that even if they're not in the same order? Like,
Yes.
Okay.
Okay? Now then, looking inside, we again are comparing x's to x's, y's to y's, and that means we're comparing numbers to numbers. 4 and 20 reduced by 4, so I have 1 in the numerator and I have 5 in the denominator. There's an exponent of 1 here in the denominator, so that means all told there are 4 more x's in the numerator, and if I compare the y's, there are 7 extra y's there. This 2 on the outside continues. Remember, I have exponents here and here, so as I distribute that 2 to the 4 and to the 1, that's going to give me 1 squared x to the 8th, which is equal to 1x to the 8th. And in the denominator, I am going to multiply 1 times 2 and get 5 squared, and 7 times 2 and get y to the 14th, or 25 y to the 14th. Okay? All right, now what happens if we get more garbage? More garbage means to continue to do the same. Just do more of it. Well, what are you talking about, Mr. Davis? Well, here's what I'm talking about. If I have 2x squared y over 3x, and I'm going to multiply that times 9x y squared over y to the 4th. Now I've got a little trick here I want to show you to do this. And it's old school. Comes from back in the days when we didn't have calculators. This 2 and 9 are going to be multiplied times each other. But as far as the x's go, I can see that there are 3 x's in the numerator, and quickly that there are 3 y's in the numerator. In the denominator, I have a big number, a coefficient of 3. I have x to the 1st and y to the 4th. Now the point of the matter is this. As I compare the y's, I have a y in the denominator. As I compare the x's, I have 2 x's in the numerator. And these values here, I don't see any sense in multiplying them just to turn around and divide them. I know that 3 divides into 9 and it divides into 3, making a 1 in the denominator, leaving a 3 in the numerator that needs to be multiplied times this 2 and give me a 6. We're going to do a couple more of these examples just to show you this little trick out here, how it works to your advantage. There is no need to multiply these numbers and make it something big that I got to turn around and try to reduce. So 6x to the 4th y squared over 4x y to the 5th times 8x squared y to the 6th over 3x cubed y. Now after I put in my unwritten ones, then it becomes repetitive. I'm going to write the 6 and the 8 in the numerator. I'm going to look at the 4x's here, the 2x's here, and add that in my head. The 2y's here and the 6y's here, and make that an 8. I'm going to write the 4 and the 3 as coefficients here, and then count up the x's to be 4 and the y's to be 6. I am then going to compare numbers, x's, and y's. And when I do, I see I have 2 more y's in the numerator. I have 2 more x's in the numerator. I see that 4 goes into 8 and 4 goes into 4. I also see that 3 goes into 6 and 3 goes into 3. So I have a 4 there and a 1 in the denominator. So all of this is over 1, which means I'm not going to leave it over 1. I'm going to simplify it to its final answer of 4x squared y squared. Last example of this type is 4x cubed y over 2y times 5x y to the negative 3 over x squared. Okay, I want you to try this on your own. Alright, this is how I did it. First of all, I needed to put this 1 in here. And if I compare my y's, this negative 3 has got to come underneath the fraction bar and become positive. So I have all kinds of y's in the denominator. I have y to the 4th. Here I have 4x's over 2x's, so I have 2 more x's in the numerator than I have in the denominator. And the 2 and the 4 cancel out to be multiplied times the 5 to give me a 10. How many got that answer? Raise your hands high, please. Okay? All right. All right, the last thing we're going to talk about is the negative quotient. Exponent. Now, this property says a to the m power over b to the n power raised to the negative p. The trick and the shortcut is that this flips. So I have b to the n over a to the m, and the exponent on the outside becomes positive. When it does, then I follow the old rules and multiply those exponents, b to the np over a to the mp. Now, why is that? Well, here's why. If you don't remember this rule, and you do it this way I'm showing you right now, it's fine. You're going to get the same answer, and that's part of the reason why I'm showing you this example. You normally would multiply this exponent on the outside times the exponents on the inside, which is going to give me a to the negative np when I multiply a negative times a positive over b to the negative np when I multiply a negative times a positive. Then you know these negative exponents have got to move across the fraction bar and become positive. Well, I just followed the rules here. I didn't do the shortcut, but you can see that these two are the same answer. So you can learn this or not. It makes no difference. It's a shortcut. If you don't want to use it, don't want to worry about it, just want to keep it simple, try to remember less and apply it all everywhere, then that's fine. Okay? So if I have the example, and this is why you want to know the shortcut, because this flips the fraction on the inside, makes the exponent positive, and I know from here this is then 4 cubed over 3 cubed, and I realize many of you don't put in this step, but that's okay. 4 cubed is 64 over 27. Likewise, using the trick, 2x squared over y cubed raised to the negative 2 power, flips the fraction, makes the exponent on the outside positive, and then I can make this y to the 6th, 2 squared, x to the 4th, which is the same as y to the 6th over 4x to the 4th. Okay? I got 2 more examples. 2 more examples. And they are double stars. The first is b to the negative 4 over b cubed raised to the negative 2. Now I've told you earlier that we have to follow the rules and order of operation, and we have to simplify inside the parentheses if we can or should. So before I ever consider this negative 2 on the outside, I'm going to make the inside of this fraction with all positive exponents. This is going to give me, then, simplifying the inside, 1 over b to the 7th to the negative 2, which is going to allow me to flip that to b to the 7th over 1 and take this exponent and make it now positive for a final answer of b to the 14th. So the reason it's a double-starred example is because there's stuff for me to do on the inside of those parentheses before I take and even think about using that negative exponent on the outside. Always, always, always follow the order of operations. Always, always, always do what's inside parentheses first. Here is the last example. Raising this to the negative 3 power. Again, doing what's inside. When I compare the x values, I have 2 more in the numerator, 2 more x's, and I have 3 more y's in the numerator. That is over 1 raised to the negative 3 power. If I want to make this exponent positive, I've got to flip the fraction on the inside and turn that to a positive. Obviously 1 cubed is 1. 2 times 3 is x to the 6th. 3 times 3 makes this y to the 9th for my final answer. All right? Everybody cool with that?